So we're going to introduce number theory today, the very, very rudimentary parts of number theory, the parts that are necessary to understand why public key cryptography works. And that's our goal. And we're going to do all this unit for that one destination, to talk about cryptography. And in order to start out, we're going to talk about a puzzle that I mentioned last time briefly. A puzzle where you have two jugs, one of size, say, 7 and one of size 17. And you can pour water, some fluid, back and forth between these jugs, and you want to figure out what various different amounts you can get by pouring water back and forth between these jugs. So the classic puzzle that's even in one of these movies recently is where you have a 5 and a 3, right? A 5 and a 3, and you're supposed to get 4. And in fact, with a 5 and a 3, not only can you get 4, but you can get 1, 2, 3, 4, or 5. You can get any of the numbers. What we're going to do here is we're just going to work with 7 and 17 as a particular example to understand this puzzle. And we're going to connect this puzzle to the fundamental first result in number theory, something about greatest common divisors and Euclid's algorithm. And from there, we're going to move on toward fancier stuff. Okay, so the question is, here's 7 and 17. What numbers, what values can we get sitting here in the 17 jug? Well, let me give you the answer in advance so you know what to look for, and then we'll actually experiment with it and discover why these things are true and prove all these things being true. The result in advance is that the different values you can get in the 17 are any multiples of the greatest common divisor of 7 and 17. The greatest common divisor of 7 and 17 is 1. So any multiples of 1, which means any number, 1, 2, 3, 4, 5, up through 17, you can get here. If I had it this way, 6 and 18, the greatest common divisor of these two is 6. And that means the only values I could get sitting in the 18 jug would be multiples of 6, which means 6, 12, and 18. Okay, that's the secret. That's the answer to this puzzle. So now the question is, why is that true? What does this puzzle have to do with greatest common divisors? And in solving this puzzle, you will get an understanding of the proof of why Euclid's algorithm works and what greatest common divisors are and how you compute them quickly in a better way than you could if I just presented it straight, theorem proof, theorem proof. So going through this and making a little list of numbers will really, really help a lot. Okay, questions so far? Okay. Well, let's review how we solve this. We talked about this once, I think, before Thanksgiving. A little bit. The way we solved it basically is we just started filling up one jug and pouring it into the other, repeatedly doing that, and we noticed how many units were in the bigger jug. So we'll call that strategy the 7 to 17 strategy. Just taking buckets and buckets filled with 7 and pouring them into 17. And we're going to notice what values end up in 17. So at the beginning, there's nothing in 17. We'll call that 0. And then we pour 7 into 17. So there's a 7. What's the next number? 14. Now it's a little bit complicated. Now we pour 7 into the 17. And 3 are necessary to fill up the 17. Then we have to empty the 17 out. There's always an implicit emptying anytime anything gets full. Because if you don't empty at that point, you've got a useless container. And there's nothing else you can do except empty it. You can't take anything out. It's not allowed. All right? So you just can empty it or do nothing. So when it hits 17, you empty it. And there's how much left in the 7? There's 4 left in the 7 because we've used 3 to fill it. And now you take that 4 and continue pouring it into the 17, leaving you with, if I did it right, 4? And then it goes up again. I'm going to need a longer place to make this list. I'll just continue here. 11. What's next? It goes up to 18, right? So there's 1 left over. There's a fast way to calculate this. What these numbers really are multiples of 7. But when you get to 17, you subtract off a multiple of 17. So these numbers are what we sometimes call multiples of 7 mod 17. Mod 17 means you care only about the remainder with respect to 17. So anytime you go over 17, you wrap around. So you can get these numbers quickly without imagining in your head the pouring, but just doing the arithmetic. 7, 14, 21. 21 is 4 bigger than 17, so it's 4. 11, 18. 18 is 1 bigger than 17, so it's 1. Everybody get it? All right, so tell me the next gazillion numbers.
8, 15, 15.
Oh, wait. 8, 15. I got to check you. 5. I'm going up here. 12. 2, 9, 16, 6, 13, 3, 10. 17 is the same as 0. Whee! There you go. That's the list. The list is exactly 17 numbers long because every number appears exactly once there between 0 and 16. Or it should. I think it includes everything. It's all the multiples of 1, which is the greatest common divisor of those numbers. So if you believe my result, it really should be every number exactly once. All right, questions so far? All right. The only other way to do this problem, there's really only 2 ways to do this problem. If at any point along this method you back up, you're just going in reverse, or you've lost all the water in your pile and you have to just start from scratch. So there's only one way to really do this puzzle is keep going. If you back up, then you're really doing the opposite strategy, which is a 17 to 7 strategy. I'll put that here. And in a 17 to 7 strategy, the same thing happens, but you get different numbers, the same numbers, but in a different order. So if we go 17 to 7, what's the first number in the 17 jug? 10, right? You pour 17 into the 7, there's 10 left in the 17 jug. What happens the next time? 3. What happens the next time?
13, 6.
All right, what's going on here? Why? What's actually happening here? How come? What's going on? Let me list them out. 10, 3, 13, 6, 16, just right? 9, 2, 12, 5, 15, 8, 1, 11, 4, 14, 7, 0. Back to 10. What's happening here? Right, in this example, we're getting multiples of 7 because we keep putting 7 more in the thing of 17. But here, what we're really doing is taking away 7 every time. Every time we go into 7, we're pulling 7 out of the 17 jar. So these are negative multiples. And that just gives you the same list, but in reverse order. That's kind of what you'd expect from a negative sign in front of an equation. All right, so this is just the beginning. We're ready to make the next step. Are there questions so far? Okay. Here's what I'd like to do before we move on. I want to make the connection to greatest common divisors here and why they show up. And here's one way to make that connection. While we go through this procedure from 0 down here to the greatest common divisor, which shows up here in a seemingly magical way, what I want to do is keep track of how many times we filled up that 7 in order to pour it into the 17, and how many times we emptied the 17 in order to accomplish this task. Okay? So do it. Do it in your heads. How many times did we fill up the 7 in order to do that? How many times did we take away the 17? The first part is easy. How come? Just count. 1, 2, 3, 4, 5, right? You filled up the 7 5 times. That's what these numbers are. Every single time means you've poured another 7 in. How many times in that process did we have to empty the 17? Once here, right? once going from here to here, and once going from here to here. Anytime the numbers go back down, it means you emptied out a 17. So we can represent that in the following way. 5 times 7 minus 2 times 17. It's not surprising that that equals 1. That just represents what we've done in order to get to this point in the puzzle. We filled the 7 5 times, we emptied the 17 twice, and we were all done doing that. We had 1 left in the 17. You could do this for any one of the rows. We're going to concentrate on the greatest common divisor one because I'll tell you why in a second. But we could do this for any of the rows, keeping track of how many we filled up each one. Questions so far? If I told you in advance I knew a way of combining 7 and 17, with a positive number and a negative number in order to get 1, say I told you 5 times 7 minus 2 times 17, you could have gone ahead and known that there was a solution to this puzzle. Because if there's a way to combine these things, then there's a way to move the buckets one way to the other to get that way. So these two things are kind of the same. But how do you come up with these numbers? Where does the 5 and the 2 come from besides doing the puzzle? Is there another way to get these numbers? The answer is there is, and we'll talk about it in a second. Before we do that, let's say I showed you a way to get 1. How would you know you could get 2?
Add 2 of those things together.
Do 2 of them together. Do it again. Make it 10 times 7 minus 4 times 17. Double it. How many more times would it take us in order to see that 2 in the bucket? If we double this, then instead of filling the 7 5 times, we filled it 10 times. So just count down 5. 1, 2, 3, 4, 5. There's 2. 1, 2, 3, 4, 5. There's 3. 1, 2, 3, 4, 5. There's 4. I will go through these numbers in order, counting by 5s, and make sure I get every single one. And that's in some sense the reason I know I can get all the things from 1 to 17. Because if I can show you I get 1, then all I have to do is count down 5 more in my big cycle, and I will get to the next highest number. And I will keep doing this until I get all the way through 16. So from now on, we don't care about the question about how we get all the rest of the numbers. We care about how we get the smallest one. If the smallest one is 1, we can get all of them. If the smallest one we can get is 2, then we get multiples of 2. If the smallest one we get is 3, then we get multiples of 3. Let's go to this side. There's a 1 on this side also. What combination does this one correspond to? It's different than that. What are we doing here? Here we're filling up 17s, right? And we're subtracting off 7s. So it's 1, 2, how many? How many 17s get filled up? How many 7s get subtracted?
Are you counting the 0 at the beginning?
That doesn't count as a filled up 17, no. But let me answer the second question first because I think it's easier. How many 7s get subtracted? Minus 7x. Just count how many times we've done it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 times we empty out 7. And how many times do we fill up 17? Who said 5? 5? Anyone else think it's 5? Go through it and ask yourself how many times 17 gets filled. 5, right? It's any time the numbers switch their order. So it is 5. And that should also equal 1. 85 minus 84, that's 1. These are different numbers in front of the 7 and 17. This 5 and 5 is completely coincidental. Okay, it is hardly ever the same number. That's complete coincidence. These two numbers are different than these two numbers. Two different ways of getting 1 as a combination of 7 and 17. One with a positive, one with a negative. And one from this way of doing the solution and one from this way of doing the solution. Okay, questions so far? You count how many times you actually pour the 17 in. So the first time when it's filled does count. So it should be 5 altogether. Yeah. Okay, questions so far?
It seems that the coefficient connections add up to 70 in one case and 7 to the other case. 5 and 12 and 5 and 2.
Is that an accident? Whenever you notice stuff like that, you got to wonder if it's an accident. Sometimes it is, sometimes it isn't. So it's not an accident here. And the next connection to make is once you figure out these numbers, the 5 and the 2, is there a fast way without going to this chart and actually counting down of calculating these two numbers, the 5 and the 12? Now before we do that connection, let me go back to this picture. In this picture, the same as before, how many times does it take us to get to this 1? It takes us 12 times, right? So presumably, if we went another 12, we would get to 2, just like over there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And every 12 will take us up 1 more. Because every time you add in another copy, 5 17s, and take away 12 7s, that is another 1. So you add an extra 1 into your bucket. So the same thing here. It's the same idea. Well, if you get 1, you can get 2, and then 3, and then 4, and then 5, and then 6. Okay, questions? Joe, okay? Yeah, okay. You look good. Yeah, I know you are. Just making sure. All right. Next step. How do we go from these numbers to these numbers? Where's the connection? I want to show you in this example because later on when you see this stuff in general, it's going to seem too abstract and you'll lose it unless you have an example to hang on to. So here's our example. Well, maybe some of you can even see how to get there. But here's the idea. If you want to figure out how to move from this 5 to this 12, what do? You take this number, you subtract it from 17. You put it there. You take this number and you subtract it from 7. And you put it there. Now that shouldn't be a surprise, and I want to convince you that it's not magic, that it actually makes a lot of sense. Let's take 17 minus 5 and put it in front of 7. And let's take 7 minus 2 and put it in front of 17. Let's multiply this out. You get 7 times 17 over here. And that cancels with 7 times 17 over here. What's actually left after those two things cancel? Minus 2 times 17 plus 5 times 17. Plus 5 times 7. 5 times 7 minus 2 times 17. What does that equal? 1. That's what we started with. All this trick does is in a sneaky way add something and subtract the same thing. So if the original equals 1, the new combination has to equal 1. It's actually easier to see this trick in general because you'll see the a's and the b's cancel. But let me review the trick again. If you have a set of numbers, 1 times 7 minus the other times 17 equaling 1, you can get a different set by taking your 5, subtracting it from the 17, taking your 2, subtracting it from the 7. Putting those two numbers, respectively, 12 and 5, in front of 17 and 7. Notice they reverse the order. One that used to be positive becomes negative, one that used to be negative becomes positive. And it also equals 1 because what you've really done is really added 7 times 17 and subtract 7 times 17 to the total. You're going to see this idea again and again, but I want you to see it first in this example. Are there questions about it? Everybody okay? Okay. I want to go slow here, and you're going to get review. If you haven't gotten it now, you'll have another chance to grab it later. But look at it now and make sure it makes sense. Questions so far? Yeah, Teresa.
Is there something you can say in the real world about this reciprocity between these going between the 5 and the 2 and the 5 and the 12. I mean, that's like the key idea that you've got, because in essence, all you've done is you've shown two ways to solve the same problem of reversing the jug size. And you've come up with equations for the two, and then you've shown how to go between them.
Right. The fact that there's two different solutions to this equation, remember ADU ball and the fact that you could get certain scores with it? The reason why you can get certain scores in that problem is exactly because there are two distinct ways of solving this. And it's going to be crucial in understanding the solution to that problem and understanding these two different ways.
So you need both ways.
You need both ways, right. And you'll see that when we get to that problem later today.
Okay.
In the actual cryptography stuff, you don't really need both these ways. You need a theorem that builds on this. The cryptography stuff is not going to use this directly. It'll use a theorem that builds on top of this. It'll use a theorem called Fermat's theorem or Fermat's little theorem to distinguish it from his last theorem. It's a theorem that Fermat came up with about modulo numbers and relates to this. But we're not up to there yet. We got a ways still. Other questions?
You can see the,
Yeah,
can
Chris?
you see the 7 one? I mean, you know the list is 17, and you know it's in reverse order.
Yeah.
So counting that many steps back from 17 in your left method is going to be the same as counting that many steps forward from 0.
That's true. I mean, going forward here is going reverse there. So there, going forward is doing multiples of 7. Here, going forward is doing multiples of minus 7. Doing multiples of minus 7 mod 17 is also the same as doing forward, well, you tell me. Minus 7 is what with respect to 17? When you're doing modulo, 0 all the way up to 16, right? So if I go minus 7, 1, 2, 3, 4, 5, 6, 7, where do I hit? What number is this? 10. So going back by 7s in modulo 17 is the same as going forward by 10s. 10, 20. 20 mod 17 is 3. 13, 23. 23 mod 17 is 6. 16, 26. There's a very, very regular pattern here. There's not too much going on once you look at it, but if somebody just shows you the sequence to begin with, you might not notice that pattern. Okay, questions? More questions? Good questions so far. Anything else before we shift gears a teeny bit? We're going to shift gears to talk about Euclid's algorithm, but it's not really shifting gears. Euclid's algorithm is going to get right back to the question of what does having a combination of 7 and 17 with a plus and a minus equaling 1, what does that have to do with 1 being the greatest common divisor? And Euclid's algorithm is a way of showing that those two are identical. If you have two numbers, 7 and 17, and you can combine them in a combination, this number times 7 minus this number times 17, and you can get 1, that means 1's the greatest common divisor. Okay, so find the greatest common divisor, just figure out a way of getting that linear combination. So in order to convince you of this, I need to tell you what Euclid's algorithm really is, and then a way of using it to backtrack up and get these coefficients in front of the 7 and 17. So the best way for me to do this is to show you an example with 7 and 17. Euclid's algorithm, like a lot of the stuff you end up learning about Euclid, is always kind of the last thing in one of his books. There's 13 books in his Elements, and this is one of the last things in one of his books on ratios, and it shows up again in one of his books on arithmetic. And it's kind of the climax, so it's something that he thinks was really cool. And it basically works like this. I won't present it to you the way that he did because it would be obscure, but I'll present it to you the way you'd think of it as a scheme programmer in a recursive way. In fact, I'm pretty sure it's one of the page 4 of Sussman's book. He must have this example somewhere, does he? All right, so it's a classic recursive algorithm. Here's what Euclid says. Euclid says, look, if you give me two numbers, 17 and 7, for example, then the greatest common divisor of these two numbers is the same as the greatest common divisor of these two other smaller numbers that I will tell you how to get. And here's how to get them. Take your smaller number and use that as your bigger number for the next pair. divide the smaller into the larger, and take the remainder for the smaller number of your new pair. So 7 into 17 would give you a remainder of 3. Euclid says, and he proves, that the greatest common divisor of these two is equal to the greatest common divisor of these two. Right? We're not going to prove it for a couple of reasons. It'll take away from the flow of the lecture. It will tell you something that is completely true and has been known true for thousands of years. There are clear proofs written in your book and every other book in the whole world on number theory, and you can look it up, and you can prove it. So take my word for it now, and we'll just continue. If these two are the same as these two, then Euclid's algorithm suggests the recursive style. So who was the first one to use recursion? You can argue, till the cows come home about who did it first, but this is clearly a recursive idea, and it's thousands of years ago. So these two are going to be the same as 3 and 1. And actually, you can take Euclid's a step further. These two are the same as 1 and, what's the remainder of 1 divided into 3?
0.
No remainder. So at this point, Euclid's algorithm would stop, and he'd say the greatest common divisor is sitting right here on the left side of the 0. This method always works. So before I show you what this method has to do with those linear combinations, I want to make sure everybody gets the method. This works for any two numbers to get the greatest common divisor. It is much faster than the following method, which your typical 8th grader would think of understanding greatest common divisors. The typical... how did you do this? How do you do this even today? Hardly anybody does Euclid's algorithm if you pick them off the street. You can do the little Jay Leno, thing. Which way is north? But ask people, which way. How do you figure out the greatest common divisor of two things? Forget actually doing Euclid's algorithm. They're not going to be able to do it at all. But let's say they could do it. How would you do it if you picked an 8th grader off the street? How would he pick out the biggest number that divides these evenly?
Try dividing by 2, and then try dividing
Right. He'd try dividing by 2, try dividing by 3, and sooner or later he'd get the highest one that divides them equally. And if you were a little bit smarter than the typical person you pull off the street, then instead of starting at the low end, he might start at 60, right? You got no chance starting over 60. Too big. So you can start at 60 and go down. And then the first one that works, that's your biggest one. And when you discover that, the average young kid is so pleased that he doesn't have to start from 1 and go up and go all the way to 60, that he can just start from 60 and stop when he gets it right, that he or she feels like that's a big breakthrough. But from a point of view of an algorithm, that breakthrough is squat. Because let's say the greatest common divisor is really 1. That's the worst case. Then this better algorithm, sure, it works better in some cases, but in the worst case, it's going to go all the way to the bottom and try just as many as you did when you were going on the way up. What's more, how many steps does this take? Let's say you can do a division in a microsecond. Right? So you got to do 2 divisions each step, and you got to do 60 of them. So the time complexity of this algorithm, of the take somebody off the street algorithm, is time proportional to the smaller of these two numbers. Okay? So if I asked you to figure out the greatest common divisor of these two numbers, well, first you'd have to count all the digits to figure out which one was smaller. Right? I think this one's smaller. And then you'd have to do 518 million steps. Okay, so even on our powerful computers, this would take some significant amount of time. This algorithm is not so good. It's slow. So how fast does Euclid's algorithm go? One of the interesting things about Euclid's algorithm is that it's not so easy to analyze. Nobody's really thrilled to do it on these two things. But if you did do it on these two things, I could give you a general ballpark of how many steps it would take. A general ballpark of how many steps it would take, more or less, is approximately the number of digits in the smaller number. In other words, about 9 steps. And I'm saying about in a very unrigorous way. In other words, it's proportional not to the size of the number, but to what? To the log base something of the number. It's actually not log base 10. That's why I said kind of fuzzy. What I said was log base 10, but my log base 10 is fuzzy. It's a different log. You want me to tell you what it really is? It's a cool theorem. I'm not going to prove it to you, but I'll tell it to you. It's also in your book. It's called Lame's theorem. And it basically gives you a sense of how many steps Euclid's algorithm takes in the worst case. Figure out all the Fibonacci numbers until you get a Fibonacci number that's bigger than this. Okay? Count how many steps that's a, what Fibonacci number that was. Is it the 15th? Is it the 7th? Or is it the 8th? The number of the Fibonacci number you have to get up to in order to get bigger than this, that's the maximum number of steps Euclid's algorithm takes. So it's actually more than 9, but it's probably, I don't know, it's probably like no more than double 9. I don't know the Fibonacci number that's bigger than this, the smallest one. It might be the 20th Fibonacci number. It might be less. Any of you who know, if Sam were here, he would tell us which Fibonacci number it was. All right, and everyone understand that theorem? Fibonacci numbers are exponential growth. So this is really the inverse of the Fibonacci numbers, which means it's a logarithm growth. And it doesn't have a particular base. It's kind of this peculiar Fibonacci base. So it's not really base 10, it's something else. But it is proportional to the number of digits in the number, not the number itself. So Euclid's algorithm is much better than the naive algorithm. It's much faster, and it really, really is maybe the first good example of an efficient algorithm.
Could you just real quick go over how the algorithm works? I wasn't quite sure.
Yeah, I'll do it on this pair.
Okay.
I'll do it on this pair.
They're both visible in mine.
Are they? Oh, yeah, I guess so. Well, all right. The truth is, like I said, 10, 15 steps with this, but who wants that? Let's do this one. This is easier. Take the smaller one, put it here. It becomes the bigger one of your next pair. And divide 60 into 128, and what's the remainder? 8. That's the next pair. The greatest common divisor of 128 and 60 is the same as the greatest common divisor of 60 and 8. Intuitively, I mean, I didn't prove it to you, but intuitively, this isn't a big jump. I mean, whatever goes into 60 is going to go into 60. Whatever goes into 128 is going to go into the remainder of something that divides into 60. I said I wouldn't prove it, and now I'm kind of pseudo-proving it. I'm not going to do it, but it's not such a big jump. It's not such a hard proof. Here's the next step. 8 goes into 60. What's the remainder? 4? Not 4/3.
4.
All right, last step. 4, 0. So the greatest common divisor here is 4. All right. Now we have to get to the connection between Euclid's algorithm and the fact that if the greatest common divisor of two numbers is a particular number, then you can compute a linear combination of the two numbers, one with a plus, one with a minus, that gets you that number. I'm going to convince you that that's true by doing it in a completely mechanical way in this example. My mechanical method will be completely general. So it won't be a real rigorous proof, but it essentially is a rigorous proof. I'm going to show you it with complete generality, but I'll show you it with a particular example, so I don't have to write A's and B's down.
Could you just repeat what you're...
Yes, I'm going to prove to you that that if these two have a greatest common divisor of 1, that I can multiply this by something, subtract those two, and get 1. Okay?
Yeah.
So here's how we do it. Let's follow Euclid's algorithm through and keep track of what actually is going on. After this step, we know that 17 equals 2 times 7 plus 3. Okay, I'm writing the details, the background details. I copied 7, I calculated the remainder. That's how you calculate the remainder. You divide 7 into 17. It goes in twice. You got a remainder of 3. Okay, 17, 2 times 7 plus 3. What do you get from the next step? 7 equals 2 times 3 plus 1. Good. What's the last step? 1 is 0 times 3 plus 1. This step is kind of like just kind of the base case. It's not even so interesting. So we actually don't really need this case. to show what I want to show, I can stop right here. Here's the 1 that I'm looking for. Here's the greatest common divisor of the two numbers. I'm going to show you how to take this sequence of divisions.
Technically, wouldn't we have another step in there? 3 equals 3 times 1 plus 0? Because we were, the second line was 7 equals rather than 3 equals something.
Oh, no, you're right. You're right. I'm going to ignore it just the same, but you're right, Doug. 3 equals 0 times 1.
3 times 1 plus 0.
3 times 1 plus 0. Right, that's exactly what I'm going to do. But I'm going to ignore that step, so don't look at it. I don't need that step. It's when I get down to here that I can stop and make something interesting happen. So here's what I'm going to do. I'm going to convince you that if I can go through these steps of Euclid's algorithm and end up with a 1 at the end of my last step where I know that there's no more to go, then I'm going to go backwards now and come up with this linear combination equaling 1. And my linear combination is going to be a combinations of 7s and 17s. Now, when you see this, it's going to seem really straightforward, but I have to tell you that whenever I teach this, people always look at it, they nod their heads in complete, okay, I completely get it, and then when they look at an example themselves, they always forget how to do it. So make careful notes when you look at this, because it's a little bit tricky, and I'll do another example later to make sure everybody gets it. Here's what we're going to try to do. We're going to work our way backwards. We're going to start with this equation and write down 1 equals 7 minus 2 times 3. Well, that's great. Now I have a linear combination of things multiplied by 7 and 3 equaling 1. But what I really want is a linear combination of things multiplied by 7 and 17. So I don't want 7 and 3 here. I want 7 and 17. So what's the thing that I don't like? I don't like that 3. Okay, that 3 is no good. I want that to turn into a 17. So now go back up a stage, and you can get a combination that relates 3 to 7s and 17. I'll write that over here. 3 equals 17 minus 2 times 7. And I'm going to take that combination that helps me get rid of my 3 and replace it with 7s and 17s. And I'm going to replace it here where the 3 is that I don't want. And here's what I get next. 1 equals 7 minus 2 times 17 minus 2 times 7. So look what I have now. I've got a longer linear combination of just 7s and 17s. When I unravel that all, I get 2 extra 7s to combine with this 7, minus, sorry, not 2, 4 extra 7s. Minus 2 times minus 2 is plus 4. Add to this 7 gives you 5 7s. And how many 17s do I have? Negative 2. So I get 5 times 7 minus 2 times 17. That's just what we had last time when I showed you how much we counted each bucket. In this case, there were only 2 steps, because there were only 2 stages in Euclid's algorithm. But if there were many stages in Euclid's algorithm, you'd have to work your way back up a number of times. So I want to do one like that to make sure everybody gets this method, because this method of working backwards to show that the greatest common divisor can always equal a linear combination of the original 2 numbers is a key method that explains how greatest common divisors connect to that puzzle problem. Yes?
But there's also another solution.
There is another solution, right. Right.
Does that have anything to do with this? Or?
Going backwards here? When you go backwards here, you always end up getting one of the solutions. And you can get the other solution by the trick I showed you before. Right. Okay. Let's do one more example. Yeah, Joe?
When you get one solution, is it always the smaller one based upon, like...
If you do it backwards from Euclid's algorithm, well, you're asking if the 7 always comes before the 17.
Like, if the smaller number would be the positive as opposed to, right, the 7 being smaller than 17.
Let's do another example and see if we can answer your question. Everyone understand Joe's question? Joe's wondering, which solution do we get? Do we always get the one where the smaller number comes first as the positive and the bigger number is negative, or does it sometimes change? You know, is there any one particular way it works out? So I think if we do another example, maybe we'll get some more data. Next example, 146. Okay, you guys help me fill in the chart. The greatest common divisor of 146 is the same as the greatest common divisor of what two numbers? 46 and 8. 8 is the remainder of what you get when you divide 46 into 100. 46 is copied over. So you all see the recursion here, right? The algorithm for these two is the same as the algorithm for these two. You just make the numbers smaller. And the numbers get smaller fast. They get smaller as fast as Fibonacci numbers grow. All right, 46, 8. So the next pair is 8, 6, and then 6, 2, and then 2, 0. Let's follow our method by writing down what each of these lines mean. This means that 100 equals 2 times 46 plus 8. This means that 46 equals 5 times 8 plus 6. This means that 8 equals 1 times 6 plus 2. Look what happens. The remainder here becomes the multiplier here. The remainder here becomes the multiplier here, until finally you get down to your greatest common divisor at the very bottom, and we're there now. So this is a 3-step process rather than a 2-step process like we had before. So we'll have to do one more iteration back in substituting to get 2 equals some combination of 100s and 46s. By the way, can anybody in their head guess what these two constants are? I mean, when I use small numbers, you can kind of do it in your head. Right? When I did 7 and 17, you know, if you try long enough, 5 times 17 minus 2 times 7, and you get the 1. But for big numbers, it isn't always so easy to guess these things. All right, well, let's go ahead and do it while you try to ponder and see if we can go backwards here. So how do we go backwards again? Remember, we start with our bottom case. We start with 2 equaling a linear combination of 8s and 6s. So 2 equals, I'll write it here, 8 minus 1 times 6. And we don't want that 6 there. We want to get rid of the 6. So we substitute in place of the 6 a combination of 8s and 46s. 6 equals 46 minus 5 times 8. So this becomes 2 equals 8 minus 1 times 46 minus 5 times 8. Did I do everything right so far? Let's rewrite this so it doesn't get too ugly. 2 equals, what's the combinations of 8 and 46 there? Who can do it? 6 times 8, right? Minus 1 times 46. But that's not right either yet, because we want just 46s and 100s. So which number do we get rid of now? No, not 46 yet. We still have to get rid of the 8. We want to keep 46 in the end, right? We want to get rid of that 8. How do we get rid of the 8? We want to turn it into things with 46s and 100s in them. Well, there it is. That line tells us the relationship between 8s and 46s and 100s. So 8 is 100 minus 2 times 46. 2 equals 6 times 100 minus twice 46 minus 1 times 46. So 2 equals, now you can combine everything together. Do we do it all right? Did I make any mistakes? I hope not. No. Minus 12 minus 13 46s. Is that right? And 600s. So 6 times 100 minus 13 times 46, that's better equal 2. And now you've got a linear combination of 100 and 46 equaling 2, which is what I promised you we could get if it was the greatest common divisor. So what do you think, Joe? What do you think about your question before? You asked before, when we did 17 and 7, whether the smaller number always appears in the positive constant.
Right, it's not true.
It's not necessarily true. Right, everyone see that it's switched here? Maybe if you have an even number of steps, the smaller one's first, and if you had an odd number of steps, the smaller one's second. Maybe. There's a conjecture. Well, I'm not going to tell you if that's right or not, but it kind of seems like it might be right. I mean, every time you switch, the negatives become positives, the positive become, maybe there's something there. Maybe that's just a lot of baloney. Maybe it's one more slice off the baloney tree. I don't know. I'll leave it for you to think about. But anyway, you get one solution, and we can get the other solution by the method I showed you before. So let's write the other solution down here to remind you how we do that. Who remembers how to get the other solution? Instead of 13 here, what do we use? Use the difference between 13 and 100. Use 87. And instead of 6 here, use 40. Yikes.
And that's guaranteed to be the smallest in that order?
Yes, but now we have to say what that means. You jumped right ahead to what I'm going to talk about next, Kristen. It's a good point, but hold off with it just for a second. The question is, what does smallest mean? But the answer is yes. Yeah, we're making progress. All right. Questions? Okay so far? All right, so Chris raised the question, which I want to formalize exactly what it means. And the question is, what are these numbers? Is there anything special about the 6 and the 13 and the 40 and the 87? You know that you'll get one solution by using Euclid's method and reversing backwards, and you can get the other solution by this relationship I showed you before. And the question is, well, number one, are there other solutions? Are these the only two?
Double them, triple them, right?
You think there's a lot? You think there's more than two? Think there's more than four?
I think there's an infinite number.
You think there's an infinite number? Well, you got to trust Chris, right? I mean, he never says anything unless he's pretty sure. He's right. There's an infinite number here. He's right. There's an infinite number of solutions here. How do you get another one? Maybe it's not so obvious how to get another one. He was kind of, Chris has a very good intuition. He goes, yeah, you double it, you triple it. You know what happens when you double this? You get 4 over here. No, it doesn't quite work, but the good thing about having a good intuition is that there is something there. You just got to figure out what it was.
Double and subtract the one on the right.
Oh, that's interesting. What happens if you do that? That'll work, right? Doug's got a good idea. Is there a more general way? I'm going to write something up on the board to give you the most general way we can write solutions to that.
Reverse it back to the...
Here. Now we're going to do... Sooner or later, I have to resort to some abstraction. Here it is. Let's say the numbers we work with are A and B instead of 46 and 100, instead of 7 and 17. A and B are the two numbers we're given. X and Y are the two linear coefficients that we make our linear combination in order to get the greatest common divisor of A and B. Okay, so just to make sure that nobody's lost, let's make sure that everybody knows that in this case, if, say, A was 17 and B was 7, then what are the X and the Y?
2 and 5.
Negative 2 and 5.
All right, the negative 2. X and Y are supposed to be positive numbers. Otherwise, I'd have to switch the negatives around. So you got to do the other solution for me. What is it?
5 and 12.
5 times 17 minus 12 times 7. Right? Remember we did both solutions there? So here we get 5 times 17 minus 12 times 7, and that equals 1. The greatest common divisor of 7 and 17. So when I write this down in general, I'm really thinking of this in particular. Now let's write down other solutions. In fact, we're going to write down all the solutions. Here, go. Massage down his neck. All right, here we go. Oop, I'm jumping ahead. Look at this equation. What happens when you multiply through this equation? You get a times x minus b times y. What's left over? Let's look at just the plus situations. Plus nba minus bna. They cancel each other out. If I add any multiple of b here and add the same multiple of a here, I get a new solution. Let's do an example. There's nothing like an abstraction to take away your intuition. Let's do an example over here. Just use the abstraction to help you here. We've got 17 times 5, and we've got 7 times 12. And we're going to use this identity and add on multiples of b here. So multiples of 7. Pick any multiple you want, your favorite multiple of 7. Don't pick 17. 42 times 7. And here we're going to pick 42 times 17. And I claim that this is going to also be equal to 1. Because it's the same as 17 times 5 minus 7 times 12 plus 42 times 7 minus 40. Plus 42 times 7 times 17 minus 42 times 7 times 17. Now you could actually calculate this if you wanted to. 17, what's 7 times 42, you munchkins? 280, who picked this number? That's a little tricky. Somebody work on this while I work on this. 7 times 42, 280, 294, 299? Help me. Yeah? Minus 7 times... It's just 299 plus 420. That's 300 plus 419. That's 719, right? 719 in this, 731. There. That better work.
Yeah, it does.
That equals 1, right? So anyway... we leave that for the reader.
7 times 9 is 63. If you do the first number, so 7 times 1 is 7.
Oh, Jesus. What did I mess up here? What's 42 times 17? 420 and 299.
No, it's 294 because you added the 5 earlier.
Oh, thanks. So this is 726. How's that? Got a chance now?
Yeah, that's good.
That's good. Okay, thank you, Michael. Good. Now I fixed it. All right. I'm kind of teasing here. I mean, you can all do the arithmetic, right? Yes, it's lucky they didn't test on that particular thing in my PhD oral qualifying thing. Okay, here's the point. Chris is right. His intuition's right. You can get multiples, but it's not multiples of those equations that we first saw. It's multiples of b's added to this x, and same multiple of a's added to this x. And what's more, you can do subtractions the same way. This actually gives you all the solutions. There aren't any others. I'd have to prove that to you, but that's true. There aren't any others. So which two are we getting when we get these? Chris had the sense that they were the smallest. Well, what does that mean? I want to convince you that smallest has a meaning. And what that meaning really is. Let's look at this. Since we can add or subtract multiples of b here, let's say we want this whole thing to be positive. You can subtract or add multiples of b until it's the smallest positive number possible. Right? If it's negative, add multiples of b. If it's positive, subtract multiples of b, just up until you go negative. You can add or subtract multiples of b until this combination x plus or minus nb is going to be the smallest positive number that works there. Let's figure it out here. What's the smallest positive number that's going to work here? Well, if we subtract off a multiple of 7, we're negative. If we add multiples of 7, we're bigger than 5. So 5 is actually the smallest positive number of the form 5 plus or minus 7 multiples. Same thing here. If you subtract off a multiple of 17, you go negative here. So 5 and 12 in these examples, in this example here, really are the two smallest positive numbers that would fit here in this form. Where you don't ever want to get negatives, just keep subtracting off multiples of b here and multiples of a there. So in that sense, 5 and 12 are the smallest numbers at work. So I'm going to write this out rigorously here. You can always pick, say, w and u, where aw minus bu equals the GCD. And I'm going to give you restrictions now on w and u. They're both positive. W is positive. And smaller than what? Smaller than any multiple of 7 in this example. Smaller than any multiple of b. And u is bigger than 0 and smaller than any multiple of a. In this way, we can say something very specific about the two solutions that we want to get. We want to get x and y, or u and w, in such a way that the w is between 0 and b, and the u is between 0 and a. And we can always do that. We can always do that because of this identity. We can always subtract off multiples if we're too big, or add multiples if we're too small. So write that down, and maybe I need to do an example, because up till now I think everybody was kind of with me, and now I get like, whoa, what's going on? Let me tell you, since I don't want to spend too long not thinking of this example. I can always do it in recitation later. But let me tell you what will always happen. If you use Euclid's algorithm, you will get one of these solutions with these restrictions. These restrictions will always hold. If you use our method of switching to another solution, you know what that method really is? It's a special case of this. And you'll always get the other solution. What special case is it? It's this special case. If ax minus by, say, equals 1, then here's the method we did. We did b times a minus y plus a times b minus x. And we said that that equals 1. Remember, that's how we got the other solution. We took this, we subtracted it from a, right? We took the x and we subtracted it from b. If you add these up, you get the same thing you get here, and the BA and the AB, the BA and the AB cancel. So what special case of this general identity is what's going on here? What's happening here? Here's the A, right? Here's the A. Here we had AX. Here I have minus A times B minus X. That's the same as A times X minus B. So all I did to go from here to here is take off one multiple of B. And since what I had before was the smallest positive number that worked, when I took one multiple off, I went into negative land. And then I wrote it on the other side here because it was negative. And now that's the smallest positive number that works on the other side of the 0. I'm toggling around 0. I'm hovering around there as close as I can. Once on the right side, once on the left side. So all we did in that other method I showed you is a special case of this, where the n is actually equal to 1 and it's a subtraction. What happened with the b? Here we had minus by. What do I have here? Minus b times y minus a. That's what this is. So I took my y and I subtracted off a, the same way I took my x and I subtracted off b. What we do here is a special case of this more general method, subtracting off one multiple of a and one multiple of b, taking our smallest positive numbers and putting them into the largest negative numbers. Then we reverse the order of them and they become the smallest positive numbers again. Right? If you get that, great, and if you don't, look at it later. Don't worry, it's not going to kill the flow that's coming up.
So would that not work for a non-lowest one then? For a higher one to use that method to convert it?
You could use this method to get any other solution, but you wouldn't reverse the 2 necessarily.
Oh, it wouldn't reverse the 2.
It wouldn't reverse the 7 and the 17 from 17 and 7. But you'd still get another solution. It would just be smaller positive numbers with a 7 and 17 in the same order. ADU ball is a problem that I gave you on who knows what, problem set 1 probably, right at the beginning of the year. And there's a lot of ways to analyze that problem. You can do it by induction. You can just take a particular example and throw it at people who are first learning to do proofs without knowing any kind of induction. Just what's the best can you do with this? And now we're going to completely solve that problem. And it's going to use these tools that we just learned. Okay, and that will kind of complete this whole unit on Euclid's greatest common divisor. Okay, and then I'll quit today. What we're going to do next time is add Fermat's little theorem on top of this, move on to cryptography. All right, so let's do this example today. Here's the ADU ball problem. You're given a game where you can score 7 points or you can score 4 points. And the question is, what are the possible total scores that you can get? You can get multiples of 7 plus multiples of 4. Right? What are they? And it turns out that if the 2 possible scores you're given have a greatest common divisor of 1, if they have a greatest common divisor of 1, then here's the solution to that problem completely. The number of different scores you can get is anything from 7 minus 1 times 4 minus 1 and up. Anything equal or bigger to this number you can get. So this is, what is this? 6 times 3, which is 18. You can get 18 and any number higher than 18. You cannot get 17. Otherwise, we'd say you can get 17 and any number higher than 17. So you can't get 17. You might be able to get some of the other numbers lower than 17, but you're not going to get a continuous sequence of numbers from 1 point to infinity until you hit 18. From 18 and on, you're safe.
I think Sam showed us you get exactly half the numbers lower than 18.
Oh, that may be true. Yeah, Sam has some other interesting problems. Like, for example, for the numbers bigger than 18, how many different kind of scores can get each number? That's a different question. For the numbers below 18, how many of them can you actually achieve? And Chris says that Sam proved that it was half of those numbers. Okay, I imagine that's true, but I don't see why right away. We're not going to concentrate on any of those generalizations. We're going to concentrate just on the straightforward problem. How do we know we can get 18 and above? And we're going to do 2 things here, part of which will be good review for those of you who still feel I don't get mathematical induction. And for those of you who feel that you do get it, it'll be good review anyway. I'm going to try to go through a proof by mathematical induction to show you that I can always get any number with 7 and 4. So it's going to be a phony proof. And you got to figure out where this proof breaks down. I'll show you where it breaks down. But in this case, the place where it breaks down is going to give us a real clue as to actually figure out where it doesn't break down. And when we try to nail down where it doesn't break down, that'll bring us back to Euclid's greatest common divisor that we just finished talking about. So it's all going to come together. We'll solve ADU ball. And I should tell you in advance that if you add one more score here, that this whole method doesn't work anymore and it becomes a much harder problem. So 2 scores, we can handle it, but 3 scores, it's tricky. Yeah, question, Chris?
Is that generally 7 minus the
It's 1 minus,
GCD?
1 less than this, 1 less than this. Multiply them.
No, but is that because 1 is the...
Yes. This theorem is not true if the greatest common divisor is not 1. The greatest common divisor must be 1.
Okay, you don't just get to replace 1 with the greatest common divisor.
No, not that I know of. I don't know whatever theorem is true for when the greatest common divisor isn't 1. I'm not sure what it is. But I bet you can come up with a nice generalization, but we're not going to do it today. So let me write the theorem out. If you're given AB, where the GCD of AB is 1, then for every n bigger or equal to a minus 1 times b minus 1, there exists an x and a y such that ax plus by equals n. We'll call this the ADU ball theorem. And now you know why I never write theorems on the board. Because all you do when you see stuff like this is write it down, you lose track of what we're thinking about, and most people aren't used to seeing things like this and making sense out of it. But this is the way you'd write it down. Given a and b, where the greatest common divisor is 1, then for every n greater than or equal to a minus 1 times b minus 1, there are two numbers, both greater than 0, such that a times the first plus b times the second equals that n. Okay? That's what we're trying to prove. All right, questions? Okay? All right. I'm going to do a phony proof by induction, then I'm going to fix it. Here's my phony proof by induction. Oh, here's my base case. Where's my base case? Base case. I'm going to show this is true for n greater than or equal to a. Okay? So my base case is use one a and no b's. Okay? So my base case is a. Check. Okay? So I'm going to show something that isn't true. I'm going to show you can go from a all the way up to anything you want. And here's my proof. My base case is a, and now I'm going to assume that n equals some combination. You know what? I think it's better if I don't do it with a's and b's. I'm going to do it with, what did I start with, 4 and 7? So my base case will be 4, and I'm going to assume that n is 4x plus 7y. You know what? X's and y's are going to confuse people because I used them before for greatest common divisor. So I'm going to use r and s. Okay, so we're going to assume this is true, that you have some number equal a combination of R4s and S7s, and it equals n. And where do we have to get to n plus 1? Everybody with me so far?
What was the base case?
Base case is just 4. Use 1, 4. We can score 4. R equals 1, S equals 0. So n equals 4. R equals 1, S equals 0. Check. Yeah, Heather, what?
Are you saying, okay, your base case is just n. If you're doing it with 4 and 7, you want to start at 18.
I would, but I'm making a phony proof that starts from 4. And I want you to show me at what point here I make a phony step.
Oh.
Right, I'm not going to prove this by induction the right way. We're not even going to fix it. We're just going to make something that doesn't work and leave it that way. Whatever you say, right? There's a reason that I'm doing this. You'll see. It'll make the way that it does work make more sense. Okay. I got n as a multiple of 4s and 7s, and now I want to get n plus 1. Big question mark. Well, here's where Euclid's greatest common divisor comes back into play. If we know that the greatest common divisor of 4 and 7 is 1, then we know two things. 2 times 4 minus 1 times 7 equals 1, right? Remember, we can write those. I did that fast. I did that in my head. I didn't go through the whole algorithm, but you get that from the algorithm. What's the other pair? What's the other solution? 3 times 7 minus 5 times 4. Remember how to get that? Some of you do. How do you get it?
4 minus 1.
4 minus 1 gives you the 3. 7 minus 2 gives you the 5. Okay. So there are two solutions. We know they're true. Well, I'm going to use these because they're going to be really helpful. I'm going to add 1 to n. And I'm going to add, say, this part to the 4r plus 7s. So I'll get what? I'm adding 2 4s here. So I get 4 times r plus 2 plus 7 times s minus 1. Right? 7 times s minus 1. And there's n plus 1. Woohoo! I'm done, right? 4 times something plus 7 times something.
It's only if you can score negative points.
All right, so Chris has an objection to this. He says it's only if you can score negative points. What does that mean? Well, this is definitely positive, right? I added 2 to r. R is positive. That's our assumption. S is positive. That's our assumption. R plus 2 is positive. S minus 1, is that positive? Not necessarily, because S could have been 0, could have been 0. And then that would be negative. So this is a complete phony proof. This is a proof which started with an assumption that n equals 4 times r plus 7 times s, where r and s are bigger than or equal to 0, and then proved that n plus 1 equals 4 times something plus 7 times something, where the two things are not necessarily equal to 0. So you went from your inductive assumption to some other thing which was not what you were trying to prove. We didn't get a strong enough proof here. This has to be positive for this induction to work. Otherwise, we haven't proved the n plus first case. We've proved some other theorem. So I'll say, okay, well that didn't work. I'll try this one then. It also equals, now I get 3 extra here, right? 7 times s plus 3. And what do I get here? 4 times r minus 5. Oh, but here I get the same annoying problem. This one's fine, but this one might not be fine. Right? So we can't fix this proof unless we could guarantee that either s was bigger than or equal to 1, or r was bigger than or equal to 5. So now we've gotten a big hint as to what number this is going to work for. This is going to work as long as s is bigger than or equal to 1, or r is bigger than or equal to 5. Maybe that gives us some kind of clue. But we're going to stop here to try to fix it. And we're going to work in a different direction to actually see which numbers will have this criterion working for them. Okay. So we're almost done here. Let me stop for a second. Other questions? We're going to fix this proof. This proof now stinks, and it's not true, and you can't get every number just from A or 4 all the way on up. So what's the smallest number that you can do this trick for, that you can do this inductive idea, and that you can use Euclid's algorithm for? We're going to calculate exactly what that number is, and that number better be, in this case, 18, and in general it's going to be a minus 1 times b minus 1. Let's say I have a number, 4r plus 7s. Instead of going our way up, which we realize doesn't always guarantee us that we get numbers bigger than 0, let's try to work our way down. I mean, we know that this works for, say, I don't know, 20, right? R equals 5, s equals 0. Let's work our way down from 20 and try to figure out the first place where working our way down doesn't end up giving us a legitimate answer. The first place where that happens, that's going to be our base case. Otherwise, it'll always work fine on the way down. Let's find the first place on the way down where it doesn't work okay. So instead of working our way up and getting some open-ended kind of thing, let's work our way down and figure out the first place where it messes up. Working our way down will correspond to taking away 1 instead of adding 1. This is not an inductive proof anymore. This is just logically trying to find the spot that works, trying to prove this theorem. So how do we take away 1 now? We can use either of these again, right? We can use this one or this one. Let's use the top one. Then we'll use the bottom one. Who can tell me what you got? You're going to take away 1 from both sides, so you're going to take away this. You're taking it away, so it's going to be 4 times r minus 2 plus 7 times s plus 1. Everyone agree? What happens to the next one? 4 r minus 4 times, Oh, it's not 4 times R, it's 4 times... Did I get it right? R plus 5 plus 7 times S minus 3. Is it right? Did I get that right? Are these backwards, R and S? Is this right? Everything's fine? Good. All right.
So the 5 and the S look exactly the same.
Oh, the S and the 5 are the same.
R plus V, right. Okay. We want these two to have positive coefficients. These two are fine. These two are not necessarily fine. Okay? When are we going to have trouble? We're going to have trouble when either this is negative or when this is negative. Agreed? So when won't we have trouble? When this is bigger than or equal to what? If this is 2, we're fine. And if this is 3 or more, we're fine. So the only time we're in big trouble is when this is less than, when R is less than 2, and both these have to be true for us to be in trouble. We're in trouble when R is less than 2 and S is less than 3. If R is less than 2 and S is less than 3, let's take the smallest situation, or the largest situation where that can happen. That means S is 1 and R is 1 and S is 2. If R is 1 and S is 2, what's the N? 4 times 1 plus 7 times 2 is 18. That means if you're at 18 and you try to go down one step, you are in trouble. But if you are above 18, then you're completely fine. This is not a proof by induction, but it proves the theorem. It says you can go from any number down 1 as often as you want until you get to 18, and then you are dead. And then you cannot, in general, do it. You might get lucky once in a while, but you can't, in general, continue. Now, we could do the whole argument here with A's and B's. And, well, I feel like, let's see. I'll just Xerox it and let you see the argument with A's and B's. The argument with A's and B's is the same as what I did here with 4s and 7s, but it's got A's and B's in place. It looks a little more abstract. I'll Xerox it right away. So let me stop here. Are there questions about what we've done? We've done greatest common divisor. We've shown the connection to that water puzzle. We've shown the connection to the ADU puzzle. We've shown a connection to a proof by induction that doesn't work. We fixed it.